train, which is in the which is like hanged on the ceiling. So this is all programmed automatic. So every single step, the chips should be taken from one step to another, one step to another. There are a series of steps, like primarily 10 steps, and these 10 steps will be cycled again and again and again to make a thin film transistor and connection of it. And on average, a single chip takes around 3 months for getting fully manufactured. So we need to wait for 3 months to get a single chip. So of course there are parallel chips. There are like hundreds of chips fabricated in a single disk. So we just end up getting those hundreds of chips. So yeah.
Sir, are you changing the slide, because we are not we are seeing the slides? Only one slide is there.
I changed the slide because I'm just giving an introduction about chip. I just changed it.
Thank you. Thank you.
Thank you. So we're all backed on silicon, but so silicon has a drawback. Silicon has a drawback in chip manufacturing. Till now, not, because Moore's law was true. They are beyond a particular limit. Beyond a particular limit, we cannot make a transistor smaller and smaller. So let's say people who are into physics, they would definitely know something called as quantum mechanics, a mechanics which is governing the very fine particles, very fine particles. So the problem is we're all talking about the gate. Traditionally, when the chips were made, let's say they're telling it's a 30 nanometer chip, they're just talking about the gate thickness, the source, gate, and the drain, the three important components of a thin film transistor, basically a MOSFET. They're talking about the gate's thickness, so how big the gate is. So nowadays, people changed it completely, because they can't like exponentially reduce the size of a gate. It's very, very difficult. So just for the namesake, they just end up telling it's a 5 nanometer transistor, it's a 3 nanometer transistor. I think recently there is a 3 nanometer transistor. So it doesn't mean the gate is 3 nanometer. It's probably 12 to around the 12 nanometer range. That's what I came to know. But just for the marketing purpose, they just end up telling it's a 3 nanometer transistor. So there is a physical limitation. There is a limitation in laws of physics claiming 5 nanometer. Beyond 5 nanometer, gate thickness cannot be smaller. If it is smaller than that, then then the transistor will always turn on. It's always on. That's how it will end up, because of quantum tunneling effect. So that is where the limitation is. So of course we need other materials, which either uses quantum mechanics or uses some other theory, some other physics to make a transistor. So definitely we can't. Let's say we will end up like 3 into 2 chip will only have this much potency. Let's say this much processing capability. It may not be more than that. We may stop. The Moore's law will end. So we definitely need smarter materials, or let's say advanced materials for these kind of things. There is so much research that's primarily in making a transistor. So in Singapore, I was trying to make a molybdenum disulfide based thin film transistor. So like this, there are so many people working on making transistor. I think in India, hardly, I think 5 to 10 institutes would probably do R&D in transistor, because it's usually very cost intensive research, and it takes a lot of cost, basically, because of the high tech equipment. So we have some other candidates apart from silicon. There's something called as silicon carbide. There's something called as gallium nitride. These two guys are the next, let's say, good materials for making a transistor, basically making a processor. So I want you guys to, this presentation is all about introducing various new materials which are in the lab, basically, which are in the lab. So I just want to tell you guys, so I think you can imagine how the world would potentially change after completing this talk. The first guy is graphene. So I think graphene, people would definitely would hear, apart from materials people or physics or chemistry people. Apart from it, I think engineering people would definitely hear about graphene now, because graphene has come into like every R&D sector. If it's an engineering, if it's, let's say it's civil, there is graphene into it. If it's mechanical, there's graphene into it, and of course chemistry, physics, material science, biotech. These everybody uses want to potentially use graphene because of their very interesting properties. It's just a single atom thick, basically. So graphite is just a book of carbon. So there are multiple carbon sheets which are stacked one above the other. So they are all attached to something called as an yeah. This is a book. Better to use this book. So this is a or log book. So this is a graphite. So this is what we call it as a graphite. It's a basically like there are single sheets of carbon which is attached one above the other. Uh, there is a physical interaction. There's a physical interaction of this guy. There's a physical interaction of the sheets of carbon. So we call it van der Waals force. So there is no chemical bond. So it's easy to peel. So the first guys they discovered graphene in the University of Manchester. Two professors and their team. So can anyone tell me how would they probably graphene from graphite? Basically a book of carbon, and they should just extract a single sheet. Can anyone come up with this idea? How would they probably extract graphene? So I'll just get you some. Oh yeah. So anyone can come up with an idea how to extract graphene from graphite? So I just got the equipment, high-tech equipment in my hand. Can anyone tell me maybe some guess or something? Okay, so I'll just tell. They use a magic high-tech equipment, which is this. It's just an Scotch tape. So they literally called it as a Scotch tape method. So let's say this is a sheet of graphite. So they just stick the sheet on a Scotch tape. So yeah, this is actually a Scotch. So you just put it on the surface, and then you just remove. Can you see? Just a thin layer of paper has stuck. So after this, so let's say there are let's say 1,000 sheets of graphene sticking onto one another. You use a tape, and you will just end up, let's say, probably you would have some 800 or let's say 200 based on the force, and it's just an trial and error experiment. So the next thing what they're gonna do is they're just gonna take this 800 sheet of graphene, yeah, graphite. So and then again stick another Scotch tape on it, and again rip it off. So you got a much thinner sheet of uh, paper. So graphene basically. So they just keep on doing this experiment, and at one point it would just end up into a single sheet of carbon. So probably definitely we cannot see it in our eyes. So graphene is like transparent, this conducting, and very strong, chemically inert, and stable. Materials people thought it's unstable. So it was very okay. So it was very new thing for the world, how the graphene was made. So graphene is made using various techniques. The most commercially, like let's say electronically, we're talking about processors. So I need to I need to introduce you to an synthesis methods, which was electronically very useful. It's CVD system. Hello. Okay, someone. So it's a chemical vapor deposition technique. That's how it's usually made. So graphene was introduced a decade back to the world. but still there is no strong real world applications because the problems is making the manufacturing cost of graphene is very high. Using a CVD system is not easy. It's of course expensive. Using a CVD, you will only end up into getting a single sheet of graphene on a substrate, basically let's say silicon wafer on it. So that's the problem. So there's another modified methods. We can usually do it chemically. This exfoliation which I talked about is physical. The Scotch tape method is a physical exfoliation technique. There's another technique which can be done chemically using sulfuric acid, hydrogen peroxide mixture. So that will end up into getting graphene. The two will end up into getting into graphene. But it's like because of these chemicals, it would end up into forming something called as graphene oxide. So definitely their properties are a little bit different, and they can once again be reduced chemically to be made into reduced graphene oxide. So the guy, the person who was making silicon, he also does this graphene, reduced graphene oxide, and he does it in the US. So they have some potent uh, they have some potent applications for it, engineering applications for it. He just bought us some samples. So he just bought a paper, his company's letterpad, and he hot pressed coated reduced graphene oxide on the sheet, and he tells it's thermally stable. The normal paper it will become thermally resistive to heat. So the paper can withstand, can bear high temperature on that side where graphene is coated. So it was very interesting. And he tells graphene RGO, reduced graphene oxide, is used in civil engineering applications in the US to increase the strength. As it's chemically made, it should definitely be far more cheaper. And many of the researchers who would probably want to do on graphene would definitely have done this modified Hammers method, which is a chemical method. They would definitely show performances of graphene. There are countless literature focusing on it. So this guy is actually a conductor, a superior ultra atomically thin conductor. So this one thing which we need to make an advanced transistor in the world. We need a very thin conductor which is stable and chemically inert. It's a marvel material. It's a marvel material. So recently there is a company in Europe which makes a graphene-based Hall effect sensors. So Hall effect based sensors are being supplied in the world by that company using graphene CVD technique. So for engineering applications, definitely we need like a gram scale or definitely gram scale. So for that, these chemical methods could be of good use. So even I was thinking, in a company, we want to make RGO and cell. So maybe that in the future. Currently, we are working on other commercialization of other materials, which they were just introduced. So after graphene, after this guy was introducing the world of 2D materials. 2D is basically an ultra thin sheet. Just to make you simple, it's a 2D material. So apart from graphene, there were other materials which were very unique, having very unique properties. Very importantly, electronic properties like metal dichromagites. It's a family of materials which is it has a metal in it and it has two chalconogides in it. Chalconogides are nothing but sulfur, selenium, tellurium. These three are something which is easy. There's the other thing which is very radioactive, so we don't use that. So these three things are basic: sulfur, selenium, and tellurium. These three chalconogides, when it's dichalconogides, if a metal and two selenium or sulfur or tellurium bind, it ends up into a crystal structure which has a sheet-like morphology, basically like graphite. So it can be exfoliated. Similarly, even MOS2 can be exfoliated using a Scotch tape method. And there can be chemical exfoliation techniques. I personally have worked in MOS2. I did physical exfoliation using ultrasound, very high frequency ultrasound. So they just they just break, they start ripping the sheets apart. So and then we used to separate it based on the size and the thickness of the sheet, and we were trying to make a thin film transistor out of it. So MOS was a breakthrough in materials world. After graphene, with this guy's single sheet of MOS2, they made a transistor, working transistor with it. So after that, the whole materials science community was crazed on these kind of material, and even now we are crazed because just a single atom thick can become a transistor, not just single atom. Okay, few atom thick. Let's say it's just an 1 nanometer, 2 nanometer, or 3 nanometer thick film can work as a transistor. So their potency is phenomenal. They're stable. There are other kinds of 2D materials like phosphorine or a black, like then germanine, and then boron carbide, then GC3 and 4, carbon nitride, graphitic carbon nitride, then phosphorus is there. And a few more are MXenes and new class of 2D material, MXenes. These are like crazy materials which has unique properties. The main reason because it is atomically thin, so they have a quantum confinement effect on their thickness. So it's 1D. The one dimension of it is having quantum confinement effect, while other two doesn't have. So basically, I'm talking about they're all nanomaterials because they're atomically thin. They have a potent application because they are giving new properties. For example, MOS2, a single sheet will have a different electronic property. A two sheet MOS2 will have a different electronic properties. Their band gap, everything changes. Their absorption, the light absorption, basically band gap. For even some jump from direct to indirect band gap and the indirect to direct, and these are crazy phenomena or things that we are seeing because of this quantum confinement effects. A combination of bulk property and a quantum confinement. That's how a nano became very famous, just because of this. They're sometimes they're having the properties of an atom or a molecule. Sometimes they're having the properties of bulk material. So he is like a nano world is like a bridge between quantum mechanics and classical mechanics. So classical mechanics, we are all governed by it. Quantum mechanics, the subatomic particles. So nanometer is like a quasi guy. So some of it possesses both the properties and it gets us unique things. So that's about the family of 2D material. So MOS2 simply by changing the thickness of the sheet, you can control the band gap. So MOS2 based photo detectors have been shown in the laboratory scale. Transistors have been shown, thin film transistors have been shown, even solar cell has been shown with MOS2. And other materials like phosphorine, basically a phosphorus based 2D material, or boron based 2D material, they're all like a little bit unstable guys. We just need to work in a glow box, basically an inert atmosphere condition. Otherwise, they are not stable. They will end up reacting with the air, and their properties completely collapse. They're not really very stable. So graphene MOS2, tungsten disulfide, tungsten diselenide, very good guys. Very good guys. Very, very stable. Very stable. So the next class of smart materials, which I want you guys to be introduced, is a perovskite semiconductor. So perovskite is the name of a scientist, a Russian scientist called Perovsky, who was giving an explanation. Who found out the structure of a class of material ABX3. That's what is the general formula of this crystal structure. So they have it's a very unique crystal structure. So I just want to, I think you can see there is a crystal structure here. So this is a very unique crystal structure for electronics, especially for solar cells. They have been a game changer. They are in the laboratory scale, not on the practical world. Still, there are many difficulties in it. But on a laboratory scale, it was a game changer because in 2017, 2018, everybody was crazy on it. Even now, but the charm has a little bit reduced. Why people were crazed on it is within like 5 years of making a solar cell out of a perovskite based material. The material was methyl ammonium lead iodide. So this was the first material which showed good performance. So today's commercial solar cells has an efficiency of 20% on an average, 18 to 21. That's how it is. So what I want to tell us, let's say you're just hitting 100 watts, 100 watts in a unit area. So you can only convert 20 watts to power. 20 watts to electricity. The remaining watts is lost as heat inside the solar cell. So it's not 100% efficient. This is the biggest drawback in the silicon solar cells. And there are other drawbacks, like, they are not flexible, they are very rigid guys, like a glass-like thing. You need to handle carefully, and the panels are very bulky in nature, and they are expensive. I think that is why most of us still thinking uh, to not take up solar panels in our house, because the investment is very huge. And as usual, we never the why the cost is high is because we never make solar cells in India. Even a solar cell we don't want to make, because of course it's a high tech process. Same like an fab, but fab is too much of technology, too much. It's a too high tech, too high tech. But solar cell is also high tech. It needs a clean room, and it needs some of the deposition units like sputtering, and all these things. Chemical based systems are needed. So we also don't do it. China is the world's largest producer of solar cell, and of course we are importing from them. I hope soon we want to make silicon solar cells in India. I think government should strongly promote that. So it's a good thing that government has promoted to make processor. That too, we realized only after the pandemic, or only during the pandemic, when there was a lack of chips. We just realized how bad it's affecting our economy. Only then we took this good step. Definitely to produce solar cell, India should definitely support. From the government side, they should support industries to make a solar cell, because it's not easy. We need clean water, we need clean air, which is a big question mark in our metro cities, and of course in tier 2 and tier 3 cities today. That's how the situation is. There's no clean water, there's no clean air for humans. And where will we go for a solar cell? Where will we go for a chip? That's the scenario. Yeah, the chips are like the plants are to be located, three in Gujarat and one in Assam. So that's the plan. We will probably have a first Indian made chip. And it's a good thing. And solar cell, the silicon solar cell I'm talking about. The problem with these research grade materials are they are highly unstable. Perovskite, if you're fabricating it, it just works for 1 or 2 days, and after that it just goes off. The material is very unstable. Methyl ammonium lead iodide will just become lead iodide. They will just break apart, and the whole structure is deteriorated. Why perovskite and these kind of solar cells, which is very important, or which is why the government is funding for R&D, is because it's easy to make. Even in my lab setup, I can make a perovskite solar. It's easy to make, because they are based on a thin film technology, by coating in solution processing. Just take, let's say you take an ink of perovskite material and just coat on it. Maybe printable solar cells is another game changer. Like, let's say you're just having your HP printer and you're loading the materials. Let's say A, B, C, D, which will be made into a solar cell. You can just print it. You can just print a solar cell in a paper. That's how powerful a thin film solar cell technology is. The problem is about their efficiency. The problem is about we need much more smart materials and stable materials. That's the biggest problem which we have in front. Of course, there are printable technologies in the research atmosphere, but the stability is the big question. Perovskite can easily be made into printable systems. You just make a perovskite based ink, you just print it on the paper and just heat it at very low temperature, you would get the active material. But the problem is about how stable it is. Let's say if the thin film solar cells are standardized, let's say we are able to make at least 5 to 6 years or 10 years stable systems, we can easily make it in India. That's how low tech it is. When compared to silicon, so I don't want to tell it's low tech, but when compared to silicon. So there are many other kind of solar cells, like quantum dot sensitized, the dye sensitized, these kind of system, and thin film solar cells. Of course, it needs a high tech thing. It can also be made low tech, like printable systems or like roll to roll processors. So the next important guy is organic electronics. So, and even organic materials, so basically carbon-based materials, even they possess semiconducting nature. It's a very interesting thing. First time when they were, making an polyacetylene, that was the very first conducting polymer which was reported. But they just, polymerized the acetylene gas. They are unstable in nature. Polyacetylene is not stable. That's why I don't think in the R&D lab anybody would use it. But that was the first reported conducting polymer. A polymer which is conducting, crazy, crazy. Crazy thing. These things we never imagined it was possible. So the plastic pen can become conductor. That's why I want to make it simple. So even we have conducting polymers in our lab. Even we make some conducting polymers. The advantage of it is they can be flexible. The systems which is made up of conducting polymers, conducting polymer based electronics, they can be flexible. So tomorrow you just can make electronics on your shirt, which is flexible and still it will work. Let's say you can build a phone on it. Probably this is too crazy to tell, but maybe because of our smart materials or advanced materials, we may end up getting such systems. Probably very much possible. Very much possible. We can make like a wearable sensors, a sensor which is like artificial skin. You just need to put it. It will stick it on your skin, and it will do all the sensing things. Let's say it needs to sense your heart pulse and many let's say electric signals in your body can be done. Can be done. Can be done. The thing is, as it's a polymer, it's very flexible. That's what the main thing. I mean, apart from conducting polymers, there are semiconducting polymers. Let's say P3HT, P.PSS, which can be tuned. This can be tuned, but of course, the physics is completely different. The band gap and everything is not there. It works on different mechanisms. The traditional guys, apart from silicon, who's like very promising, is silicon carbide. The problem is the cost. The making a silicon carbide, an average temperature should be around 2,400 to 2,600, that range. This is too much, too much. Even silicon, it's 1,400. I think most of the furnaces which we have in the lab will go only up to 1,200. So in our facility, we are planning to purchase a 1,800 degrees Celsius furnace. So we can make materials on a broader spectrum using such a thing. But this guy, silicon carbide, needs 2,000, 2,400 to 700. This range of temperature. It's too much high to process. Of course, the cost will go up. The silicon cost, silicon carbide will go up. And making the chip out of it and fabricating it is a little bit tedious process. Better advantage of it is good thermal conductivity, breakdown voltage, all these things. Can anyone tell me what is the limitations of today's phone? A simple question. I think that's how I need to start this content actually. So apart from the global things and all these things that was going on, so what is the daily limitations that we are facing as a normal person? Yeah, like we maybe we don't have a supercomputer. We just have a smart computer in our hands. So what are the limitations an everyday layman faces? Can anyone throw some light on it? Can anyone? Am I audible? Okay, so okay, I'll just tell. Yeah. So I'll just tell because the phone is like overheating, a very important thing. But when you just constantly, let's say you're just chatting with the team member or someone, it gets heated up. That's where the silicon carbide comes in. So this guy is like having a good thermal conductivity, so they can easily transfer the heat. Basically, how it is done is, so this is a chip. So this is where okay, this is where the transistors are fabricated. Basically, fabricated on this surface. This surface is where the heat sink is. Yeah, the heat sink is there, and above the heat sink there is the fan. That's how a CPU works. The CPU fan, right, is just staying above this heat. Silicon should actually conduct the heat, and it is needs to transmit. So it's a very important thing. When even if you fabricate an efficient transistor on it, the thermal conduction is very important. The silicon carbide has a good thermal conduction. The breakthrough voltage reach, transistor can work on a higher voltage. So these are several advantages. Silicon carbide based special processors are used in applications for satellites and high tech systems. Gallium nitride, a very important guy in history, especially for LEDs. So when you when probably when you were in your college, or like let's say a few years back, 20 years back, or during 90s, whenever we're buying an electronic equipment, you would see like a different LED bulbs, small LED bulbs are smart as, let's say, for the volume or bass or any such system, that will just tell you how much the uh, percentages. They are all either made of a green LED or a red LED. It was never made of an blue LED. Have you ever noticed? I think you would realize, by the time I have told, you would have realized. So they are making a blue LED was the biggest challenge. Even after the commercialization of LEDs, people were not able to make blue LED for a decade. It's a crazy thing to know. So the people were trusting only two guys, two materials, which would probably make a blue LED, because the band gap and all these things are difficult to bridge to make an LED. So gallium nitride and the zinc selenide, these two guys were the two promising guys for making an blue LED. So gallium nitride was the first rollout to make a blue LED. Today also, wherever you see a blue LED, there is gallium nitride sitting inside. So basically, even your phone has gallium nitride. So these pixels are just made up of, as you know, green, red, and blue. So blue is made up of gallium nitride. So gallium nitride has a potency for electronics. The thing is, when it comes to layman's thing, it's a bit costly. So even today, a blue LED is a little bit costlier than red and green LEDs. Next smart material is so silver nanowires. I want to show you because we are trying to manufacture these guys. So here in our lab, we have one of our work is making an commercially available silver nanowire ink. So as I told, we can print electronics. So we need a conducting ink for it, which is transparent in nature. For certain diodes, certain photovoltaics, these applications, we need let's say a touch sensor, let's say a touch screen. For these things, you need a base transparent conducting electrode. So commercially, it is indium tin oxide and FTO, fluorine doped tin oxide, but they are very, they're not flexible in nature. So the only flexible guy which is potent candidate in the world, the flexible for all the flexible systems. Let's say a flexible solar cell, flexible diode, let's say a flexible artificial skin. You need something to conduct, right? Maybe it should be transparent, and you don't want it to be seen by others. Definitely, silver nanowire is an active candidate, and we are trying to actively, make like an ink. It's a precipitate now, so it looks like just a brown piece of some waste, but it's a very potent candidate in electronics. So we want to make silver nanowire inks for an R&D labs. So we are not thinking about manufacturing it to and supplying it to industries. So making such industries are very rare in India, at least for a research level, because we are not we are just a small lab, a small startup. To make it on a large scale, we need several crores of investment, at least few crores. So we're just making it on a small level. So we'll just at least sell it, make it in India, and at least sell it to whoever is need. Basically, in R&D, people needs a very small amount. So we want to make this printable ink. So that's where our R&D is, and probably we will roll out this product in a few months' time. So we have optimized the procedure to make it. So we are just looking about to make it stable ink. So such R&D is going on a small level. So this guy is very important. As I've already told you, what are the potential of to make sensors, many things, many things. They are like a backbone. Of course, nanomaterials, as I told, they have this combination of classical and quantum mechanical effects in it, and they have very high surface area. These things are advantageous for us to make materials of different nature. So as you know, silver is like it's just a silver in color, but this guy is like just like a mud. See how their optical properties have changed just because it has made into a wire. Like this weird properties are available. I'll just show you a nano silver. So this is a colloidal silver. So there is a silver, like a very small nanomaterial put into a liquid, basically water. So this is how a nano silver looks like in water. So the color and everything. I just want to tell you guys that the properties are very unique, the exhibiting because of these things. And the next important thing which we are working in our company is the production of carbon nanotubes. So of course, engineers would definitely know if they are into some kind of an R&D, they would definitely know the carbon nanotubes has potent properties to enhance the strength, enhance their engineering properties, which is needed for an engineering application and better properties. It's thermally conducting, and important thing about it is it's a very hydrophobic in nature. They don't want to stick to water, and they are very very strong. The tube is strong, and they are good thermal conduction. And thing is, it's the blackest material in the planet. So maybe you want a blackest material in the planet. Carbon nanotube is one such thing. So even we are trying to manufacture carbon nanotubes on a low-tech system. So we are collaborating with an NIT team. And we have a patent to make a carbon nanotube in a low-tech system. We are working on it to commercialize it on at least on a small scale because of the funds and all these things. So the next a very important thing is energy storage materials. In terms of electronics, without the power, where will we go? Without the usage of because today the smartphone users will definitely know that every day we need to charge. So these things, this is where the importance of battery materials are coming up. And in a period of let's say 5 to 6 years, there's so much research that's going on battery materials, energy storage materials, basically like batteries and supercapacitors. Here in our lab, we work on supercapacitors and some basic analysis for even batteries. So we can actually fabricate a battery or a supercapacitor in our facility. We have the facility to do it. So So this is the case. This is the case which we'll be using. I think you guys would know what is this. It's actually a coin cell, button cell. So we can make a button cell in our facility. So such kind of researches are very much useful and very important for us because we know how much limitations are there in our daily phone. I just want to tell from the phone so that it's much more easy for us. So the electrodes, some R&D is going on, many R&D, solid state electrolyte is going on. I just want to tell you, lithium based systems is going on, zinc ion batteries are there, sodium ion batteries are there, and zinc air battery is there, sodium air battery is there, then nickel metal hydride batteries are there. Then supercapacitors are carbon based systems like a carbon and a semiconductor mixtures like ferrites have shown very good capacitance. So usually the small capacitors which you have seen probably when you open the computer or thing, they are usually in microfarad. So people have developed several farads, hundreds and even the 1,000 farads. So which is a phenomenal amount of power. As I previously told, lithium sulfur battery is one such thing. The next thing is energy production materials. Apart from silicon, because of this manufacturing thing, and it's a tedious process. Apart from silicon, what else we can do? Various researches are going on thin film solar cells, and also the third generation systems where it uses perovskite, or it uses a quantum dot or dye sensitive material solar cell. These kind of systems, where either it can be made into a thin film or an electrochemical cell-based system. So electrochemical cell-based systems can be done in our facility too. It can even be analyzed. And another important field in terms of energy production is fuel cells. So as we know, hydrogen and oxygen will fuse together to make water, which is H2O. It is like it generates a tremendous heat during this reaction. We want to use that heat to power our to generate electricity. So basically, the final stage of rockets, the modern day heavy lift rockets. I'm not talking about PSLV or SLV or the systems which are developed now, but the heavy systems like GSLV Mark II, Mark III, then the Gaganyaan mission would definitely need a high thrust rockets because it's taking a very high payload. The mass is high, so usually they use a cryogenic system there. So we know because the hydrogen oxygen reacts together to generate enormous heat. That's where the cryogenic engines are. So we need to use that energy to generate into electricity. The beauty about it is the waste is there is no waste in the system. The ultimate byproduct of the system is just water. So many research is going on making a cheap electrodes to make this fuel cell. Apart from platinum and costly systems, we want much cheaper systems like nickel, cobalt based systems are being developed. So it's somewhat commercialized, but not to the layman's world. Still has not come to that level. There are many R&D going on the film, the membranes between the fuel cells. And there's another sector where we are working on is the electrolyzers, where you need to generate, just add water and you need to generate hydrogen and oxygen. So you just compress the hydrogen and use it for hydrogen-powered vehicles. So recently, there have been commercially running hydrogen-powered vehicles. Recently, the Karnataka government has an hydrogen-powered vehicle. So they're all based on the same system. Just mix air, burn the hydrogen, and generate heat and let the engine run. That's how it works. So hydrogen storage is an even other field where so much R&D is going on, like solid state hydrogen storage and compressed hydrogen storage and all these things. So potentially in the future, I think the three important things which is needed is driving innovation and enhance the capabilities of devices. Let's say it needs to process much more data. It needs to generate lesser heat. It needs to be very stable, and the very important thing is sustainability challenges. So once we generate an e-waste, we need to know how to dispose it. It's a very. I think that's all about my talk. So with this about my company, just a brief thing. We are just an R&D company now, working on various kind of material synthesis, characterization, and studies. We help industries and academics in their projects wherever they need a materials part. We would help them. So we have some more characterization facilities. We have an electrochemical workstation. It's just here. So we can actually, it's off. So we can do various kinds of studies. Like for a solar cell, you can study how an diode works. You can study how for a fuel cell, if the material is an active candidate or not. For an electrolyzer, the material is an active candidate or not. These kind of things, whether it's a good candidate to make a solar cell or even a transistor, these kind of preliminary studies can be done using this unit. We have an antibacterial testing facility. where we can test how, let's say we are making a new or a smart material, whether it has a good potency on the strains. Why I'm just a materials guy. I don't know nothing about microbiology, but still I just hired a microbiologist and put a small lab because I face in this situation of antibacterial resistance, which is being developed in the world. I think we are all aware of it. Traditionally, people used to give one antibiotic and we just drink it. We just take it and it will just solve. But today, that's not the case. You just take antibiotics and still the treatment would fail. So we would go for next stage antibiotic and next stage antibiotic. These are especially happening in ICUs. So when my child was born, he was having some infection, bacterial infection. So we were using a first stage antibiotics, but it failed. We used the next stage, and even that failed. And some very high potent antibiotic, colistin. So only that helped us to revive my child. So I was very affected by it, and we definitely need bacterial resistant, let's say, handles for ICUs, bacterial resistance floor, bacterial resistance bed sheets. These kind of things are very important because that is where multiple bacteria are there in the place, and even multiple antibiotics are there. So the interaction of it can definitely build the antibiotic has built. That is the reality. So we can stop these kind of things when if we are able to make antibacterial coatings for, let's say, the handles of the ICU and the stretcher and the floor and the wall. I think this is most important to make such an coatings. Very few coatings are there commercially available. One of my known person has a company. They were working on this kind of coatings materials. We have a spectrophotometer, we have a photochemical reactor. So this is the guy here. So this can help us study how a material reacts with light and how the material is performing in presence of light. Especially we are using it for environmental remediation studies, where using a solar light, we just need to degrade the pollutants. Let's say antibiotics or dyes or any kind of nitrophenol or let's say bisphenol or all kind of toxic pollutants we want to degrade using a photocatalyst. So such kind of studies can be done. Apart from it, even reactions can be done using a light use. This is my scientific advisory members. So without a teacher, I don't think nothing happens without the right kind of induction. So they're all my supporter and well-wisher. Yeah. So that's all about today's talk. So if anybody has any inquiry or discussions, can come forward. Hope I didn't take too much time. And this, yeah. And also, I need to once again thank the committee for inviting me. I need to give a special thanks to Tangaraj sir for this valuable opportunity. Thank you, sir. Thank you. Any discussions or questions are invited.
Any queries, sir, from the participant side? Hope, shall I conclude? Okay, thank you. Thank you, sir, for your knowledge sharing on the topic current trend and future outlooks in materials for electronics. Thank you very much, Engineer Arjun Murthy. And now I would like to invite the Honorary Secretary, IEI Salem Local Center, to propose vote of thanks. Please, ma'am.
Thank you, sir. Thank you, sir. Audible, sir?
Yes, ma'am. Yes.
Yes, sir. Most respected our chief guest and keynote speaker, Engineer Arjun Murthy, sir. Our respected chairman, Dr. Tangaraj, sir. Respected engineers, members from state and Salem Local Center, professors and students from various institution and organization. Good evening to all, one and all. It's my privilege to propose vote of thanks on this great occasion, Engineers Talk, a weekly online lecture series. Actually, this is the 46th webinar series. The topic is current trend and future outlook in materials for electronics. So it's my great pleasure to propose vote of thanks on behalf of each and everyone present here to our chief guest and keynote speaker, Engineer Arjun Murthy sir, founder and director, Robel Materials Research Center, Private Limited, Salem. Actually, sir, you have given much useful information about the advanced materials for electronics, current trend and future outlook. So today we had a very young and dynamic entrepreneur. It's excellent presentation and vibrant presentation, sir. Actually, this 1 hour is not enough to hear from you. So we need extra hours. In future, we'll have like this seminar. Thank you so much, sir. Thank you so much. My sincere thanks to our beloved chairman, sir, Dr. K. Tangaraj. He is backbone to of all our activities. My special thanks to our team members, Dr. Satish Kumar, sir, Dr. Kumaravel, sir, Engineer K.S. Selvam, sir, for their valuable presence. I extend my sincere thanks to Engineer Armugam, sir, for his excellent support rendering always for IEI. I record my sincere thanks to Mr. Thiagu. He is behind for organizing this webinar successfully. I also wish to express my gratitude to all the engineers, students, professors for your active participation. Once again, thank you all to make this webinar success. Thank you. Thank you, one and all.